Good morning again, Advanced Chemistry, and today we're going to talk about Learning Target 4.1, the first learning target in your new unit about acid-base chemistry. So 4.1 says that we are going to describe the basic properties, no pun intended, the basic properties of an acid or a base, and be familiar with acid-base nomenclature, so some rules about how to name acids and bases. So here we go. Let's talk about some fundamental properties of acids. So some properties of a quote acid. So what makes something an acid? If you were to taste an acid, which you do on a daily basis, acids are prevalent in foods and beverages. They have a tart or sour taste. In fact, if you look on a can of Mountain Dew, you'll find a citric or a phosphoric acid, giving it that tart or sour taste. Acids do conduct electricity in solution, therefore they are known as electrolytes or electrolytic solutions. That is because there is a partial dissociation of ions, just like our KSP values were showing, where we have some ions in solution. Acids have a slight dissociation in solution as well. Some of them dissociate completely. We'll talk about that more later. But because of that dissociation of ions, they do conduct electricity to a certain extent. Acids will react with metals to produce hydrogen gas. This would be a single replacement reaction. So I add that on here. That would be a single replacement reaction releasing hydrogen gas, so long as those metals are above hydrogen on the activity series. So anything above hydrogen on the activity series will do this. As far as the metals go, if that hydrogen is in the acid, then it will liberate that hydrogen into gaseous form. They undergo what's called a neutralization reaction with bases. So acids will do this. A neutralization reaction is a double replacement that produces a salt. It doesn't have to be salt, but a salt, which is a metallic cation and an anion, plus water. And then acids have a pH under 7. We're going to talk a lot about pH and what exactly that means this unit, but for now, your pH scale, for now you'll know that it goes from 0 to 14, and right there at 7 is considered neutral, and anything below that, 7 and anything lower than 7 is considered acidic. So those are just some basic properties of acids. Some properties of a base. And that should be a base, not an base. Some properties of a base, fundamental. These will have a bitter taste, not only in food and beverages, but in other things. I don't know if any of you got your mouth cleaned out by soap when you were a little kid. But soap has base in it, and it has a very bitter taste, not that I would know. Bases also conduct electricity, at least a little, which means they have dissociated ions to a certain extent, so they are electrolytic in solution. Some are very good conductors, some not so much. Bases tend to have a slippery feel. Like acids, they undergo neutralization reactions. I see that I have some mistakes on this slide. I know you're shocked. bases have a pH over 7. So on the pH scale, the highest recognized pH is 14. So above 7 to 14 would be considered basic. There's a common misconception that bases are less dangerous than acids, and that's not true. It just seems to be that bases are less common in things that are known to be dangerous, but bases can be just as dangerous as acids. So one thing, this says 4,4, and that's wrong. But I want you to write it down here just because I think it's a good spot to talk about it. I want to talk about what makes a strong acid or base strong. And I have strong in quotation marks there. I want you guys to know the difference between something being a strong acid base or being a concentrated acid or base. So a concentrated acid or base means a large number of moles of acid or base per unit volume. So you guys know what concentrated means. We've been talking about this since like the second day of class. So if I have hydrochloric acid, which would be HCl, I could have HCl that's 0.1 molar, or I could have HCl that's 18 molar. 18 molar is the concentrated acid, but both of these are strong acids. So there's a difference between concentrated and strong. Concentration is the molarity that you know, and we've talked about so far. Strength indicates the extent of ionization. So when I talk about a strong acid or a strong base, strong, that means that there's going to be 100% dissociation into ions of my acids or my bases. So you could have an acid that was very, very concentrated, say that it was 14, 15 molar, but just because it's very concentrated does not mean that it's a strong acid. Same thing for bases. So those two are different things that get mixed up quite a lot. So I'm going to give you a final example here. Acetic acid is vinegar that has been diluted. And acetic acid, the formula for acetic acid is HC2H3O2. So one thing I want you to notice right off the bat is that this H out here in front, that's called the ionizable hydrogen. And it's written out front, and that's how you will notice that something is an acid, is because it's actually going to dissociate from the molecule. So it's not one of these hydrogens that's going to stay intact, but it's written out front separately because it's the one that's going to dissociate. I don't know if you guys recognize this guy right here, but C2H3O2 is the acetate polyatomic ion. Acetic acid is a weak acid It's not a strong acid. So when it hits the water, what's going to happen is that some of it will dissociate and become H plus 1 and C2H3O2 minus 1, both of those being aqueous, and dissociate into its ions. But since this is a weak acid, this is not going to occur nearly as much as something that is stronger. So what that means is the number of ions in solution is very small. So you might say at equilibrium, KEQ would be very small because you wouldn't have very many ions in solution for a weak acid. But you could be starting with a 16 molar acetic acid solution, so it could be very concentrated. That means you would have more ions in solution, but still compared to the entire molecule, the number of ions in solution is going to be very small. So let's switch gears a little bit now and go to some naming. So some nomenclature of acids. And so first we're going to talk about binary acids. And a binary acid is an acid containing hydrogen plus one other element. So over here to the side, I'm going to do an example, and that will be let's do HBr. So here we have a binary acid. We have just hydrogen and bromine. So that's binary. You see our hydrogen, our ionizable hydrogen is out front, so we recognize it as an acid. The steps to name a binary acid are very simple. We're going to use the prefix hydro plus the stem of the anion, then ic at the end. So the prefix hydro, stem of anion, ic. So this is going to be hydro, the stem of the anion. This is the bromide anion. So the stem of bromide is brome, and then ic. So this is hydrobromic, and we don't need those dashes in there. So I will just write it like a normal person. And then your second step is very easy. It ends in acid, because it is an acid. So the name of HBr is hydrobromic acid. And I feel like I can just hear you guys talking about my handwriting right now, so I know it's not very nice. I'll try to work on it. So I'm going to have you try one now. All alone, all by yourself. There you go. Try it. Have your substitute pause for a second. And here's what you should have gotten. Hydro, phosphor is your stem, ic, acid. Hydrophosphoric acid. Okay, so you get some practice with those. If you don't just have two elements, because look, maybe that was confusing, but here you just have hydrogen. Yes, you have three of them, but you have three hydrogens and a phosphorus. So you have hydrogen and phosphorus, which makes it binary. If you have more than two elements, hydrogen plus more than one element, you're going to have what's known as an oxyacid. And an oxyacid is hydrogen plus a polyatomic ion containing hydrogen. or excuse me, containing oxygen. Now, there are other acids that might not contain oxygen. They're just not called oxyacids, but the rules are the same. And most of them contain oxygen. I'd like to renumber these, so these say 1A, 1B, and 2 here. What we need to look at for our nomenclature of our oxyacids is what our polyatomic ion ends in. And our options are 8 or ite. So if your polyatomic ion ends in 8, we're going to use the stem of your polyatomic ion, and you're going to add ic to that stem. So I'll give you an example here. This polyatomic ion is SO4 minus 2, that's sulfate. So when you're doing your stem of your polyatomic ion plus ic, that would be sulfuric. If 1B, your polyatomic ion ends in ite, you're going to use the stem of your polyatomic ion plus aus, O-U-S. So if you had SO3, that is a sulfite ion, you'd have sulfurous. So 8 turns to ic, ite turns to us, and then step 2, add acid. So let's do a couple of examples, and you will want a polyatomic ion sheet handy unless you recognize these polyatomic ions. So let's do together. Let's do that one, H2CO3. Well, here are my ionizable hydrogens, and there's my polyatomic ion, that is carbonate. So the stem of my polyatomic ion would be carbon. Add an ic, because it's 8. I ate it, ic. So that would be carbonic acid. Try another one. HClO. Well, there's my ionizable hydrogen. So this is the hypochlorite ion. Ends in ite. So this is going to become, well, goodness sakes. The hypochlorite polyatomic ion. So if I ite, I'm going to end in us, hypochlorous acid. So pretty easy rules to remember. Excuse me, it's been a long day. Pretty easy rules to remember, just got to practice it a little bit. Acid nomenclature will help you out a lot later on down the line. So I will leave you to it. You've got some practice problems to do, and we will check those tomorrow, make sure they're done. On the back of those practice problems, or on the second page of those practice problems, are some more Lewis structures, shapes, formal charge practice, and I will make sure the key for all of that gets on the blog tonight so you can check your answers. So have a really good day, and I will look forward to seeing you soon. Bye.